Hello everyone, welcome to Engineers Ireland. Today we're going to finish off on complex numbers. At this stage we have covered trigonometry, and that's what we were waiting for, because the second half of complex numbers brings in the polar coordinate form, and once you get that and you get into Demiverse theorem, you now have found a new method of dealing with trigonometric identities and stuff like that. So they are quite related, but trigonometry had to sit in ahead of this. Okay. Now, just before we get onto the polar form, it's important that you remember that when we draw a graph for a complex number, that we don't call the graph a Cartesian coordinate system xy, because what we're going to do when we plot a complex number is we'll plot the real bit on along what we would normally call the x-axis, and we'll put the imaginary bit up along the y-axis. So this is the real bit, and this is I, the imaginary bit, going up that way. So clearly, if you had a number, we'll say z1 equals 3 minus 2i, you would say, okay, let's go out 3 and minus 2i, so you're going to go down minus 2, and you'll be saying, there it is, there's z1. And if we have z2 equals to minus 2 minus 4i, it's pretty obvious. You go minus 2 real, and you'll be going down minus 4, so it's about there. Well, that's pretty obvious. Now, this is where we get another little bit that's a tie-in to several other chapters. Now that we've drawn a point on a diagram like this, we recognize that there is a distance between the point, a linear distance to the origin. For example, with these ones. And we normally give it this name. Now, it's the modulus of z1, and we're going to use the exact same equation that we had used in basic algebra and basic geometry, and that we've used also in trigonometry, and that is the distance between 2 points to actually work this out. Now, there's no major problem with this. We can say, if for example we have z equal to a plus bi, then now, if you were to measure something, whatever it is, the answer is always a positive number. So just because this guy is down here and we may have negative numbers belonging to it, in other words a minus 2 and a minus 4, the modulus is still a positive number, because the easiest way to think of it is it's a measurement of a length, and you can't measure minus 5 meters, for example. You have to measure a positive length. This is necessary, and it's a very important little step, because now that we've established this, the actual length, we now have a second way that we can identify a point. If we had a point there, what we did in the first diagram here is we went so far over and we went so far up to find it. Now, what we can say, let's look at it this way. Let's go that far out, and we'd say, what's the angle it's rotated at? Theta. If I know the angle, and if I know the distance from the origin, I can locate any point like that point here. So that's the second way of being able to find any point on a plane. How far away from the origin and what its rotation is from the positive real axis, the x-axis fundamentally. So then, in this case, we just call this again Z. Oops. Just Z. We're saying the length is modulus of Z, so that's good. We have half of what we need. We know how far away it is. The second thing we need to know is what's theta? What's the angle? Well, it's easily worked out because we want to find out how far over, and we know that that distance, the amount it's gone over, is the modulus of Z cos theta, and the amount it went up the way, that length, is the modulus of Z sine theta. You should be well experienced in working out those two, having come through the trigonometry and also having seen this in the polar form that came through in geometry. So then we're able to say, I can say that Z is A plus BI, or I can say that Z is equal to its own modulus outside of cos theta plus I sine theta. And mathematicians love shorthand. You get the C, you get the I, and you get the S, and they'll say this is equal to the modulus of Z CIS theta cos I and S for sine. So then you have a choice. You could say it's so much along in the real axis plus so much up along the imaginary axis, which is the traditional method, or you can say it is a certain distance out and rotated a certain distance from the positive real axis. That's the choice. Why would we try to do this? What's the advantage? Well, the advantage comes in the form of a really powerful piece of mathematics. And its proof, by the way, is on the course. But the good news is, it's not difficult. And the piece of mathematics is Demiverse theorem. So what we're going to do now is we will step a little bit closer to how we deal with Demiverse and what we need to know in advance, just to make it easy for ourselves. We can recap a little. In trigonometry, if we had an angle A like this, our job to find coses and sines, our job was to find a reference angle, and you always got this reference angle by going to the tip of whatever the radius was, drawing a line parallel to the y-axis towards the x-axis like that, so you get a right angle triangle, and we would say this guy in here is the reference angle, which we were calling R. And we can now say a number of things. Why we want to call it R is we want to find an angle that's between 0 and 90, no matter what sector we're in. We could be, for argument's sake, down here. And once we draw our line parallel to the y-axis towards the x-axis, in this case, that's the R belonging to that angle A. The 0 to 90 angle, which is R, will always have a positive cos and a positive sine. And we want to be able to equate A to that. In complex numbers, the only thing that really changes is the naming. We normally, instead of a, we talk about theta, and instead of r, we talk about alpha. They're just names. It's the same thing you've done before. So, this should not be difficult for you. A little example will help though. Okay, we want to write z, which is minus root 3 minus I in polar form. The secret to all of these things is draw a drawing. When you draw a drawing, like in any of the other sections, what you're doing is you're removing the need to conceptualize, to put develop a picture in your mind, which is very hard work for the mind, and it'll actually make you tired much faster than much of the other stuff you do. So we're going to draw a drawing for this. And what we're going to do is we're going to find the point. See, that's the point there. Now, having found the point, we will be able to, we're looking for that guy to begin with, which is the same as your reference, your R angle in trigonometry. And we are obviously looking to find out what this angle is. So then, this radius, which is basically z modulus, okay, we want to find it first. Now, that didn't hurt. It's straightforward mathematics. Now, you will notice in here that the square of a square root is just whatever the number is inside. For example, 3 is the square root of 9. So root 9 squared is the same as 3 squared, which is 9. So root 9 squared is 9. So, what else do we know? We know that length, and we know that length. Now we're talking about lengths here in relation to alpha, and even though we're down in the third quadrant, alpha is somewhere between 0 and 90, so the values belonging to alpha are actually positive values. So we're saying, I actually know the tan of this, because it'll be that length divided by that length. So alpha is 30 degrees. Because we're in the third quadrant, we now know that our theta is going to be equal to the 30 plus 180. Now, this is an important thing here. We could say that that is 210 degrees. Here's a fundamental difference in how we generally treat the angles in complex numbers relative to how we treat them in trigonometry. It is not a universal standard, but it is the one that's generally used. And what I'm referring to is, if we look at it, and we look at the angles here, we look at positive angles up to 180 degrees, and we look at the remainder of the circle is considered as negative angles down to minus 180 degrees. So our theta will sit between minus 180 and 180 degrees. So in this case we won't add the 30 to the 180 because that value is outside the range. What we will do, we'll say that theta is equal to 180 minus 30 minus outside that, which is minus 150. It's 30 less than 180. Theta equals minus bracket 180 minus 30. So we have a minus 150 degrees. And now we can actually write what z is. Remember, it's the r, which is the modulus, which could be called mod of z, outside of cos theta plus I sine theta, which we could also write as r cis theta. So in this case z is equal to 2, that's that guy up here, it's worth your while practicing a lot of these things, because then you become very fast at it, and in the exam you save time, and that is an important consideration. There are two things you learn, or you should be learning in secondary school. One is you should be becoming educated in, for example, mathematics in this case, and you should also become a campaigner, because the exam is a test, and you've got a campaign to become as good at that test next June. And one of the things you know is that, like many sporting events, you'll be checked on time. There's a time restraint. Practice now pays back in saving you time in the exam and freeing yourself up so you don't have to worry about it when you're sitting in there. So then, let's see where we go from here. As a little lead-in to Demiverse, we refer to a particular property, property 1. Now what it's actually saying to us is that cos A that if I multiply that what we will get well, that is a curious thing, because you can imagine in your mind that you would have, let's say, an r, the modulus for this first vector here, and it's getting multiplied also by a modulus of a second vector, so, or not vector, sorry, complex number. So in other words, we're saying if we want to multiply two complex numbers that are in polar form, we will happily finish up being able to go the modulus of the first by the modulus of the second. But wouldn't it be nice to be able to speed up the process of the multiplication of that and that? And what this first property is telling us is we don't have any multiplication to do. All we've got to do is add the two angles. Now, it's well worth it to go and prove this so that you can go and use something very simple. Let's set about proving it. I can multiply. Now we're only going to deal with the trigonometric side of it. I can multiply out these things and I will get now when I'm multiplying out two complex numbers, I normally will go first by first and last by last, and the reason for it is we will finish up with an I squared, and we know that that is going to transform into a -1, so they'll be the first two, and we'll say plus, and in any of the other ones I'm going to have an I, so I'm going to get AD plus BC by I. So it's first by second and second by first that gives you the imaginary bit, because this guy goes to -1. So what we get is equal to AC minus BD plus AD. So let's do it this way here. Just remove this now. This I squared becomes -1, so we have and that's the real bit, and we have an imaginary bit. And we should be able to identify these because we have just covered the trigonometry bit, and what we get out of this, that is equal to the cos of A plus B plus the I sine of A plus B, which was equal to the right hand side. So we're happy, we've proved what we wanted to prove. We've also, and one of the nice things about this little proof is it actually tells you what you're able to save yourself. If you look at when we multiplied that by that, what did we get? We got all of that, the need to remember this, break it down into this, and then having to go and see that we have trigonometric relationships, one operating here and the other operating here. All of that can be set aside now because we have proved that that's all we have to do. Instead of a lot of multiplication, we just have an addition. Let's look at an example. Okay. Z1 by Z2 is equal to 5 by 2. That's the easy bit. It's that and that. And that's going to get multiplied into. And we could have had all of that mathematics, but we don't. All we have to do now is add the angles. And I'll just change the notation to the shorthand version. And we're saying cis of 180. What's cos of 180? It's 180. The cos is obviously -1. And the sine is 0. That's a very useful, easy way of multiplying numbers. And it's just a setup for something that's a lot better, because it allows you to deal with very elaborate powers of numbers, including finding out the roots, not only square roots, but any roots, like the fifth roots, etc. of numbers. And that particular thing, which is often referred to as the second property, is Demiverse. What does this guy tell us? Well, it says to us, if I have cos theta plus an I sine theta, and if I want to multiply it by itself many times, bring it to a power of n, that all I got to do is go cos n theta plus I sine n theta. In other words, I just multiply the angle by the intended power, which is n. So that's just n times the theta, n times the theta. The interesting thing is, while this is true for a whole range of different types of numbers, the two things that we have to prove it for the Leaving Cert, and it is on the examinable side of proofs, is we have to do it for all integers, positive and negatives. What we do is we break the proof down into two parts, and we look at all whole numbers first, positive whole numbers. So we're going to look at the n, an element of n0. Now when you see this little 0 here, what does it mean? The n set, it's 1, 2, 3, n0 simply includes the 0. And we know the z set it's all the pluses and minus full numbers. And what we can also then say is that implies that the n set is equal to the plus z set. We have to be a little careful here, because even though we are looking at the n0 set, which means we're including a 0 in what we want to prove, let's just look at the caution to begin with. Let's just go 3 squared, and we're going to ask ourselves, is that the same as 5 squared? Now clearly it's not, because we get 9 is not 25. So let's look at 3 to the power of 1 equal to 5 to the power of 1. Is it? Clearly it's not. 3 is not 5. Now here's the problem. Is 3 to the power of 0 equal to 5 to the power of 0? And the answer is yes. True. because 3 to the power of 0 is 1. Anything to the power of 0 is 1. 1 equals 1. So then, when we're now dealing with Demiverse and we want to prove it for n equal to 0, we know that we could actually prove a heresy, in other words that 3 is equal to 5, if we just simply take as our first case the n equal to 0. So we look at it and we look at the n equal to 1 case. The proof to begin with, now that we've discussed this, we're now going to look at the first half of the proof now. And this is carried out using induction. We covered induction a few weeks ago, and at the time I was mentioning that it's really important because it crops up all over the place, and this is just one case in point. How does induction work? Induction is a bit like a set of dominoes. If you've got a line of little dominoes all the way along here, and if you tip this one over, it'll hit that one, which will then hit that one, and on, and they'll all fall. How does the game work in induction? It works like this. Here's a line of them, and we'll say that's the first one here, and they go on and on and on, and we'll get to this one, which will be the K one, and we'll find that yes, there's another one after it, and obviously there's going to be more and more after it, and you go all the way up as far as the N one. This is a very long line of dominoes. We're going to, for induction, we're going to prove our case for the first one, the first one that is useful to us, and we say yes, it's proved for that one. Then we're going to assume it for this K one, and having assumed it, we're now going to look at the K plus 1 case. We're going to look at this guy, and we're going to see if it's true for this one. And what happens in induction, you find that you can prove that it's true, but that proof is dependent on this guy being true. So if you get the point now, we're saying that one, yes, it's true if only that guy is true. Now, here's the odd thing. You could keep saying that all the way down along the whole line of these little soldiers, all the way along here. And you go to the last one. This second guy could say, oh, it's true for me if only it's true here. But the point is, we've proved it for the first one. So if all of these can turn to their left and say, it's true for me if it's true to you, and you go to the first one and he says, it's true, it's been worked out for me, then what happens is all the dominoes fall. That one hits that one, and all the way through, and they all knock each other out, because the first one was true, and everyone, it's the truth of it depends on the one to its left. So let's play the game. There's always 3 parts to these proofs. One is find the smallest case, which is generally called the S case. Then you assume the K case, you play with the K plus 1 until you find it's true based on it, and then you do a little word game, which is really bringing in the dominoes business. So part 1. Now, we want to prove for all positive whole numbers. That's what we're going to do using this induction. We do know that if n here was 0, anything to the power of 0 is 1. We do know when n is 0 here, we've got cos of 0, and cos of 0 is 1. And sine of 0 is 0. So we can say, yes, 1 equals 1. But remember, we can't pick that one as being our first case, because even 3 to the power of 0 is equal to 5 to the power of 0. So we haven't really proved an awful lot there. What we have to use as our first case is the s equals 1, i.e. power 1. We're going to use that one. that implies cos theta plus I sine theta, and power being just 1 means that's all we have there. Is it equal to, this is what we want to check, cos of 1 by theta plus I sine 1 by theta, and that is equal to cos theta plus I sine theta, and you can say true. So that's the first bit. Part 2. Assume the k case, i.e. what are we going to assume? We're going to assume that cos theta plus I sine theta to the power of k, we're assuming that it is cos of k theta plus I sine of k theta. And we want to prove the pk plus 1 case. And what is the pk plus 1 case? That's equal to that. We are looking now at this cos theta plus I sine theta to the power of k plus 1. We want to be able to prove that that is equal to cos So we want to prove that it's equal to the cos of k plus 1 thetas plus I sine of k plus 1 thetas. Let's expand this guy out here, the left hand side. Now, what do? We want to make it look, the k plus 1 case, to look as alike to the k case as we possibly can, so as we can bring in what we've assumed, which is the k case. I just want to bring you back to something that we spoke about in the very first class, and that was that 2 to the 7 minus 2 to the 6. What was that equal to? And what we found out then is we're going to try and make this first term look like the second term, and you'll say, well, 2 to the 7, that's 2 by 2 by 2 by 2, etc. for 7 of them. So isn't that 2 by 2 to the 6? And it is. So we now have that minus 2 to the 6. So that's a bit like saying 2 apples minus an apple is equal to 2 to the 6. That's just reminding you. When I have 2 to a power, I can always split up that power. So something to the power of k plus 1 is equal to that thing multiplied, or sorry, brought to the power of k, multiplied by itself to the power of 1, which is just itself. Now the nice thing is, we have achieved something we were wanting to achieve, which is this bit. Wasn't that the left hand side of the k case, which we assumed to be true? So we can say that implies we can put this in for it. And we can do that because we've assumed the k case. Now in your mind you can imagine that k theta is an angle A and theta is an angle B. So now you can see we're back to property 1 again, so we can actually say, oh, that is equal to, I'll put it down here, it'll be the cos of a plus b. So what is that? It's the cos of k plus 1 of these thetas plus I sine of k plus 1 of these thetas, which was equal to the right hand side. In other words, we've said we've come all the way from proving the k plus 1 case, we've brought it all the way across to this. And we're saying to ourselves, okay, we've proved the k plus 1 case. However, it rests on an assumption, and the assumption is that we could go from this to this. So the k plus 1 case is true if the k case is true. However, the s equal to 1 case is true. Therefore, this is true for all cases, for all n values. So we've actually proved it. Now, you can word the reasoning in several different ways. Each of the textbooks will have nice formal ways, but I always try to think of it in terms of the dominoes and say the k plus 1 case is true if the k case is true, but the first case is true, therefore all the cases are true. So that then is the proof of all the positive whole numbers. What we have to do now is prove the negative ones. And that's very easy. What we want to do now is cos theta plus I sine theta, that to the power of minus n, where obviously n is greater than 0. Okay? And we could say n an element of n. And by using minus n, we're now talking about negative numbers, obviously. And what we want to do is prove this. We want to prove that it's equal to cos of minus n theta plus I sine of minus n theta. And we're back into algebra again. You'll notice how many times once we move on in sections we actually get back to a point where we have to appeal to things we learnt in algebra. And what are we going to appeal to this time? That x to the minus n is equal to 1 over x to the n. This thing to the power of minus n must be equal to 1 over cos theta plus I sine theta to the power of n. Here's something else we learned. We can actually transform this part of an equation now by appealing to the factors for the difference of two squares. If you remember, in algebra we had a plus b by a minus b is equal to a squared minus b squared. Now that's the ways it works in algebra. The interesting thing is, if you look at complex numbers and we'd say a plus ib multiplying into a minus ib, that's actually equal to a squared plus b squared. And the reason for it is the I by I will give you a minus, so minus by minus will give you a plus, and we finish up the sum of two squares. And what we've actually done here is we have changed something which is a power of 1. All of these things are power of 1. We've changed that into an expression that is exactly doubled the powers, and that's what we're trying to achieve. And you'll see why now in a second. So I can say it's equal to that multiplied by 1, and I want to find a particular form of 1, something divided by something that's going to help me here. We know we can transform this based on the first half of our proof, equal to 1 all over cos n theta plus I sine n theta, and the form of 1 we're going to choose is the conjugate of this. Now look at what happens below the line, because that's the interesting bit. It's exactly the same as what we have done over on the right hand side, so we don't have to worry much about it. We can say, isn't that cos squared in theta plus sine squared in theta? And we know that the cos squared of an angle plus its sine squared is 1. All of that disappears and becomes a 1. So all we're left with is what's above the line. Sine n theta. And if we go back up to the very top line here, we can say cos of n theta is cos, or cos of minus n theta is cos n theta minus I sine n theta. So we've actually proved what we wanted. Let's just make sure you know what we're dealing with here. If I have an angle A, and this is my unit circle, and if I look at minus A of an angle, what we know is that they share the same cos. That proves that cos of minus A equals cos A. However, this is a positive sign, that is a negative sign. So we know that sine of minus A equals minus sine A. That's why we were able to go from that line down to that line. And we've arrived at it here. So we can say, now for all elements of Z, which are the positive and negative whole numbers, that Demiverse theorem has been proved. We don't have to prove it for elements of R, so that's not too bad. Let's see how useful this thing is. Let's look at powers of numbers. Z equal to 1 minus I, and we want to bring this to the power of 20. That could be a whole load of multiplying, but instead what we will do is we will find out what Z bar is, or sorry, what the Z's modulus is. So it's going to be the square root of and we want to find out its angle, and we always draw these things. So it's across 1 and it's down minus 1. So there it is. That's Z bar. And we know that that length is 1 in length and that length is 1 in length. So we can, in looking at this angle here, the alpha, we can say alpha tan alpha is 1 over 1, which implies alpha is equal to 45 degrees. That implies the angle we want, the theta, is minus 45 degrees. Because we're going to be going down this way. Remember, our angle in these complex numbers, in the polar form of them, sits between minus 180 and plus 180. That's why we're using a theta of minus 45 here. We're now in a position to be able to rewrite z. That implies z to the power of 20 is going to be equal to the square root of 2 to the power of 20 outside of Now, let's play with this guy. Root 2 squared to the power of 10. And we'll say cos of 20 multiplied by minus 45 plus I sine of the minus 45 by the 20. It's just easier to write it the other way around. Root 2 squared is 2, so that's equal to 2 to the power of 10 outside of cos. Now, 2 45s is a 90, and 10 90s to the power of 10 should be 1024. Now, cos of 900. We want to keep our angle between minus 180 and 180. So the easy way out of it is, if you divide the 900 by 360, you will find out how many complete circles are in this. Now, it's clearly 2 point something or another. And that's as far as you need to go, because 2 of these is 720. 900 minus 720, it's 180. So we can say that's cos of minus 180 plus I sine of minus 180. And cos of minus 180 is minus 1, so it's 1024 outside of minus 1, and sine of minus 180 is 0. So the answer is 1024, which is normally referred to in the computer industry as K. So then, see how useful this is. You may think it's a little bit painful, but trust me, it's not nearly as painful as trying to multiply this out by itself 20 times. This thing is a very powerful tool. Now, we can also use this to find the roots of a complex number. However, there's one little thing we have to do before we actually can apply it. While we're dealing with simple powers, in other words powers bigger than 1, we were able to just use an angle theta. Now what we have to do is we have to look at, even though this may be here and we'll say that's really the angle I'm looking at, technically you could have gone around and around and around and around many times and got to the same location. So I can say that theta is equal to itself plus n 360 degrees, or that theta is equal to itself plus 2 n pi. There won't be a change, obviously, because if you go and turn it around 4 times and you leave it at the same place, it looks exactly the same. We have to do that. So this time we have to go for the general form of the angle when we're dealing with the conversion from the ordinary Cartesian style system to the polar system. And we'll take an example just to make life easy for ourselves. find the square root of z, i.e. z to a half. Well, let's plot what we have. And we can say that length there is now clearly going to be, the square of it is going to be the sum of the squares of the other sides, because we have a right angle triangle here. So we can now tell ourselves, we call that r is equal to the square root of 1 squared plus root 3 squared. What's alpha? We know it's tan. Tan is the opposite over the adjacent, so it's the root 3 divided by 1. So we can say alpha is 60 degrees. What we're looking for is this guy, theta. Theta is 180 minus 60, which is 120 degrees. Exact same game as you were playing in trigonometry. The important thing though is it is worth your while doing this little piece over here. You take it out of the way, you deal with it, you draw your little drawing so that you will not make a mistake. So what we can say is that implies we can now rewrite things as 2, and I'll use the alternative shorthand version, okay, of 120 degrees, because that's what we found, plus n 360s. That's if we go around and around many 360s, it's not going to change the fact that the thing will finish up the same as if you had a basic 120 degrees. What we want now is to find the square root of it, of all of this. We want to find that. So we're saying it's 2 to the power of a half by cis of a half of 120 plus a half by n 360, and that's why we had to go for the general form. One last little thing to note is that number here, the number underneath the line in the power, will tell you how many roots you have. So now what we're going to do is we're going to count out our roots. What does n equal to 0 mean? It implies that the first square root of the z is equal to root 2 sorry that is a very easy method. Now you may think that you could easily find out a square root. Yeah, but we're just using a square root here as an example. We could have been dealing with the power of 1 over 5 or 1 over 17, for example, and then you'd be looking for 17 roots. Then you would have a very different game on your hands if you were trying any other system, and it would be long and difficult. Whereas this method doesn't get any harder. If you were looking at powers of 1 over 17, in other words 17th roots, you would just, having gotten down to that line here, having got down to this particular line here, you would be using 1 over 17 here. You'd finish up with an expression that will look a bit like this, and then you'd start counting n equal to 0, n equal to 1, n equal to 2, and you get 17 of them. So it stays easy. The last little thing you just have to notice is, for example, if we have 2 minus root 3i to the power of 5 over 2, that is simply 2 minus root 3i to the power of 5 all to the power of 1 over 2. So you deal with this bit first, which is easy, and then you will find that you only have 2 square roots. So even though you see an expression like this, it's always this underneath number that tells you how many roots you're going to have. All we've done there is we've said x to the a b equals x to the a power of b, which you've seen before. Now we can use these very useful tools, the Demiverse and property 1. We can use them to solve trigonometric identities. It's straightforward, and you'll find it in the books. The principle of how to use it you can see in these few examples that we've had here. The value of this, I don't think I could overstate its value. It's one of the great and powerful tools that you actually learn for the Leaving Cert. So I would expect you to go and practice a lot of this stuff. Now, the next day we're going to start on on calculus, differential calculus. And what I would like you to see the next day is just how similar it is to geometry of the line and to parts of trigonometry. And again, what you will find very quickly is how powerful it becomes. It's a nice section. Okay? See you the next day.